Okay, so now that you finished the exercises on RoofIt, I wanted to discuss one point that we asked you a question about during that exercise. So you may remember making a plot that looks a little bit like this, as you can see here on the right. And we asked you why the blue line, which was made for a Higgs boson mass of 120 GeV, and the dashed green line, which was made for a Higgs boson mass made of 115 GeV, overlap. And the reason for this is that RoofIt is very strict about enforcing ranges that we set on parameters. So as you can see on the bottom here, we've taken the example command that was put into the tutorial. We set a range of 120 to 130 GeV for our rural var MH. This means that when we try to set MH to 115 GeV, RoofIt simply took the nearest bound, which was 120 GeV, because we'd asked it to use this range of 120 to 130 GeV. And the reason we're pointing this out is that this is something that will always be important later on when you're using ranges to keep in mind. Now, having finished with the RoofIt section, we're now moving on to Combine. Combine is a tool that's used only in CMS, and it is built on top of RoofIt, but it implements some additional methods, and it also makes it easier to build a RoofIt model with some easier syntax for the user rather than doing everything by hand. And we will learn some of the main features of Combine by using a simplified version of the MSSM Higgs to tau analysis with the 2016 dataset. In this analysis, events are split into categories that target the main di-tau final states and two main production modes of BSM Higgs bosons, namely gluon fusion and B-associated production. And the category of this analysis that we're going to use in the exercises that are to follow is the B-associated production mode targeting category in the fully hadronic final state of the two taus. And you can see here on the right the backgrounds and the expected signal and also the data in that category. In part one, as we mentioned before, we'll be doing a counting experiment, and we'll only use the high mass region from about the red line as indicated on the plot on the right. And in part two, we'll use the full mass spectrum to perform a shape-based analysis. Now, the first thing to learn about Combine is how you can construct your model, and this is via the data card, which is just a text file that Combine can pass and can use to create a RoofIt model. And we just want to take you through all the different numbers and labels that you see in this data card. At the top, there are three numbers: Imax, Jmax, and Kmax. And Imax sets the number of bins or channels. So this is not the number of bins in a histogram, it is the number of channels entering your analysis. In this case, we're doing a one-bin counting experiment, so we only have one bin. And the next line, Jmax, gives you the number of processes. In our case, we have four background processes and one signal process. And Kmax gives the number of nuisance parameters. As you can see here, we've put a star. This means that Combine will determine the appropriate number automatically. And you can do the same with Imax and Jmax. You can also put stars for those. And Combine will determine the numbers automatically. The next line, it starts with bin, gives a unique label to each channel. Again, in this case, we only have one bin, so we only have one label, signal underscore region. And then on the next line, we have the number of observed events in each of these channels. Going further down, the first process line gives a unique process label to each of the processes. This is just the name of our choosing. And the next line, we give a process identifier. This is always an integer. For a signal process, the identifier has to be 0 or negative. And for background processes, we use positive integers. And the final line in this block is that starts with rate, gives us the expected numbers of events for each of the processes in this region. At the very bottom of the data card, we have a series of lines that indicate the systematic uncertainties. In the first column, we give the name of the systematic uncertainty. The second column, the type. In this case, we're doing a counting experiment, and we only have one type of uncertainty, the log normal uncertainty, but we will see different uncertainties as we move on in this tutorial. Finally, the numbers that you see are the effect that these uncertainties have on the process normalization. So for example, 1.02, which you see in the top left for the CMS FB uncertainty on the TT bar process, means that this uncertainty modifies or affects the TT bar normalization by 2%. Now, having learned a little bit about the data card format, you will start working with data cards immediately, and the first thing that you will do is add some missing uncertainties to the example data card that we'll be providing in this session. And after that, you will set some upper limits on the cross-section times branching ratio for BBH production with the Higgs tau decay for a BSM Higgs boson. Now, throughout this section, we'll ask you some questions, and they will be discussed in the next video. So please watch that video once you are done performing the exercises in this section.